Right now, the most distant machine ever built by human beings is moving through interstellar space at more than 38,000 miles per hour. A radio message sent from Earth needs almost a full day to reach it. A reply requires almost another day to return. And on November 18, 2026, Voyager 1 is expected to cross a strange milestone. It will become the first human-made object to reach a distance of 1 light day from Earth, about 16.1 billion miles, or 25.9 billion kilometers. From that point on, even light itself will need 24 hours to travel from us to the spacecraft.
That is real. What is not real is the viral claim that Voyager suddenly turned around a few minutes ago and photographed something NASA cannot explain. Voyager 1 has not taken a picture since 1990. Its cameras have been off for more than 36 years, and the software needed to operate them was removed from the spacecraft's computers. There was no secret image, no object following the probe, and no last-minute transmission showing a wall at the edge of the solar system. But the truth is more interesting than the hoax.
Voyager did reach a boundary no spacecraft had ever crossed. It detected a sharp change in the particles surrounding it. It found interstellar plasma that was denser and hotter than some models predicted. It recorded a faint, persistent hum in the space between stars. And when it crossed into interstellar space, one of the clearest signals scientists expected to see did not appear in the expected way. For months, NASA could not even say with certainty whether Voyager had actually crossed the boundary. So what did Voyager really detect? What would its camera see if it could still turn around? And why does a spacecraft built before the personal computer continue to change our understanding of the space between stars?
To answer that, we have to return to 1977. Voyager 1 was launched on September 5th of that year, 16 days after Voyager 2. The numbering sounds backward because Voyager 1 was placed on the faster trajectory. It reached Jupiter first in March 1979 and Saturn in November 1980. The original mission was designed around a rare alignment of the outer planets that occurs roughly once every 176 years. By using gravity assists, the spacecraft could steal a tiny amount of orbital energy from each planet and redirect itself toward the next target.
Voyager 1 was sent past Jupiter and Saturn. Voyager 2 continued to Uranus and Neptune, becoming the only spacecraft ever to visit both worlds. These encounters transformed planetary science. Voyager revealed active volcanoes on Io, complex ring structures around Saturn, new moons, violent storms, and magnetic fields unlike anything scientists had measured near Earth. But for Voyager 1, the decisive moment came at Saturn. Mission planners directed the spacecraft close to Titan, Saturn's largest moon. That flyby provided valuable measurements of Titan's thick atmosphere, but Titan's gravity bent Voyager 1 out of the plane in which the planets orbit. From that moment, the spacecraft was no longer headed toward another planet. It was climbing northward out of the solar system's planetary plane and into open space.
Its cameras still worked, but there was almost nothing nearby left to photograph. Then Carl Sagan and other members of the imaging team argued for one final look back. On February 14, 1990, from about 3.7 billion miles, or 6 billion kilometers from the Sun, Voyager 1 rotated its camera toward the worlds it had left behind. It captured 60 frames for what became the Solar System family portrait. In one of those frames, Earth occupied less than a single pixel, caught inside a band of scattered sunlight. That image became the pale blue dot.
Immediately afterward, Voyager's cameras were powered down. The decision was practical. Imaging consumed power and computer resources, and the spacecraft was not expected to pass close enough to any object for useful photography. Mission managers repurposed the computer that controlled the cameras, and the camera software was removed.
So, could NASA turn the camera back on today?
Technically, NASA's own Voyager FAQ says powering the cameras may still be possible in principle. In practice, producing an image would require rebuilding and uploading control software to a machine with extremely limited memory, reviving electronics that have spent decades in deep cold, consuming power that is now needed by the surviving science instruments, and taking a serious risk with a spacecraft that has no repair crew and almost no margin for error. Even if it worked, the result would disappoint anyone expecting a cinematic view of the edge of the solar system.
Voyager is not approaching a glowing wall, a new planet, or a visible ocean of stars. Its cameras were designed for bright planets and moons during close flybys. Interstellar space is almost completely dark. The Sun, seen from Voyager's current distance, would still be the brightest star in the sky, but it would appear as a point of light. Earth would be far too faint and too close to the Sun's apparent position to resolve with Voyager's old cameras. The background stars would not look dramatically different from the stars we see from Earth. Voyager has traveled an almost unimaginable distance by human standards, but compared with the distance to even the nearest star, it has barely moved. The constellations would remain almost unchanged.
If Voyager turned its camera forward, it would most likely photograph a black field with stars. No visible border, no luminous membrane, no sign saying that interstellar space begins here. The edge Voyager crossed can be detected only through physics. The Sun constantly releases a stream of charged particles called the solar wind. That wind carries the Sun's magnetic field outward, creating a vast bubble known as the heliosphere. The planets orbit deep inside this bubble, but the solar wind continues far beyond Neptune. Eventually, it begins to collide with the material between stars. First, the supersonic solar wind slows at a region called the termination shock. Beyond that lies the heliosheath, where the solar wind is slower, compressed, and turbulent. Finally comes the heliopause, the boundary where pressure from the solar wind balances the surrounding interstellar medium. Crossing the heliopause means entering interstellar space. It does not necessarily mean leaving the solar system in every sense. Before Voyager, scientists often drew these regions as smooth, nested surfaces. The real heliosheath was messier. As the Sun rotates, its magnetic field is wound into a vast spiral. Because the field reverses polarity across the solar magnetic equator, Voyager encountered folded layers of magnetic field in the outer heliosphere. Models and spacecraft data suggested that some of these layers break apart and reconnect, creating a foam-like region of magnetic islands or bubbles.
That image should not be taken too literally. Voyager did not photograph spherical bubbles floating in space. The word describes changing magnetic structures inferred from particle and field measurements, but the result challenged the idea of a simple, unbroken magnetic barrier. Charged particles may move through the boundary along complicated paths, and the heliopause may contain ripples, folds, and temporary channels rather than behaving like the smooth surface shown in most diagrams. The Sun's gravity reaches much farther than its solar wind. Far beyond Voyager lies the hypothetical Oort cloud, a vast reservoir of icy objects inferred from the orbits of long-period comets. NASA estimates that Voyager 1 may need about 300 years just to reach its inner edge, and perhaps 30,000 years to pass beyond its outer boundary.
So Voyager is in interstellar space, but it is still inside the Sun's much larger gravitational domain. The distinction matters because the edge of the solar system is not one simple line. There is an edge of the planetary region, an edge of the solar wind bubble, and a much more distant gravitational frontier. Voyager crossed the second of those boundaries, and it did not cross it in the clean, predictable way many researchers expected. By 2004, Voyager 1 had reached the termination shock at roughly 94 astronomical units from the Sun. 1 astronomical unit is the average distance between Earth and the Sun. The probe then spent almost 8 years crossing the heliosheath.
As it approached the heliopause in 2012, the environment changed dramatically. The intensity of low-energy particles coming from inside the heliosphere collapsed. At the same time, galactic cosmic rays arriving from outside the heliosphere increased sharply. These were powerful signs that Voyager had entered a new region. But the magnetic field created a problem. Most models predicted that when Voyager moved from the Sun's magnetic environment into the interstellar magnetic field, the field direction should rotate noticeably. Instead, the magnetic field strengthened while its direction changed very little. That was why NASA did not immediately announce that Voyager had entered interstellar space. The particle data looked convincing, but the magnetic signature did not match the simplest expectation.
The decisive evidence arrived indirectly. Voyager 1's dedicated plasma instrument had failed in 1980, so it could no longer directly measure the density of the surrounding low-energy plasma. But its plasma wave subsystem could detect oscillations produced when large disturbances from the Sun reached the spacecraft's region of space. In 2012 and 2013, solar eruptions sent shocks outward through the heliosphere. When those shocks reached the plasma around Voyager, the plasma oscillated at characteristic frequencies. The frequency revealed the electron density. The measured density was far higher than expected inside the heliosphere and consistent with the local interstellar medium. That allowed scientists to conclude that Voyager 1 had crossed the heliopause on August 25, 2012, at about 122 astronomical units from the Sun.
Humanity had placed an operating instrument in the space between stars. But interstellar space did not turn out to be a calm, featureless void. One of Voyager's most important discoveries began to emerge in data collected from 2017 onward. The plasma wave subsystem detected an extremely weak, narrow-band emission that persisted as the spacecraft traveled across about 10 astronomical units of interstellar space. Researchers led by Stella Ocker at Cornell University described it as a persistent plasma wave emission. When converted into audio frequencies for human listeners, it resembles a thin, changing tone, a distant electronic hum. It is important to understand what that sound is not. Voyager did not record sound with a microphone. Ordinary sound cannot travel through near vacuum the way it travels through air. The instrument measured electrical oscillations in plasma, and scientists translated those measurements into frequencies we can hear. The signal was scientifically valuable because its frequency tracked the density of free electrons around the spacecraft. Before this discovery, Voyager could estimate plasma density mainly during occasional disturbances caused by powerful solar eruptions. Those events were like brief flashes, illuminating an otherwise dark landscape. The persistent emission provided something closer to continuous measurement.
Across years of travel, Voyager mapped small changes in the density of the interstellar plasma. The data revealed structure and turbulence on astronomical unit scales. The space between stars was still extraordinarily sparse, but it was not uniform. It had density variations, waves, and traces of disturbances that had traveled outward from the Sun. This was not evidence that the laws of physics had failed. It did not prove that interstellar space is alive, and it did not reveal an artificial signal. Researchers have debated the precise physical origin of the weak emission, including whether it is produced by plasma oscillations or a related effect known as quasi-thermal noise. But both explanations belong to plasma physics, not alien technology. The mystery is real, but it is a scientific mystery. What exact mechanism creates such a persistent narrowband feature? And what can it tell us about turbulence in the very local interstellar medium?
There is another reason the region remains difficult to interpret. Voyager is outside the solar wind bubble, but it is not beyond every influence of the Sun. Large eruptions can merge into enormous pressure waves that travel through the outer heliosphere, strike the heliopause, and transmit disturbances into the interstellar plasma beyond it. Months or even more than a year can pass before the effects arrive at Voyager. That means the probe is studying the very local interstellar medium, a region that may still be compressed, heated, and magnetically distorted by the heliosphere. It has crossed into interstellar space, but it may not yet be sampling completely undisturbed galactic material. The farther it travels, the more scientists can watch the sun's influence gradually fade. The problem is that Voyager may run out of power before that transition is complete.
Voyager also revealed that the heliopause is not a perfectly smooth shell. The boundary responds to the sun's 11-year activity cycle, to powerful solar eruptions, and to variations in the interstellar material pressing from outside. Voyager 1 and Voyager 2 crossed at different locations and under different solar conditions, yet both encountered layered, complicated transitions near 120 astronomical units. Voyager 2 provided a crucial second perspective when it crossed into interstellar space on November 5, 2018. Unlike Voyager 1, its plasma instrument was still operating. It directly measured the disappearance of the outward solar wind flow and found that the plasma just outside the heliopause was denser and somewhat hotter than expected.
Measurements suggested temperatures of roughly 30,000 to 50,000 kelvins in the very local interstellar plasma. This number has inspired one of the most misleading descriptions of Voyager's discovery, the so-called wall of fire at the edge of the solar system. There is no solid wall, and Voyager did not pass through a sheet of flame. Temperature measures the average energy of individual particles. In the interstellar medium, those particles are extremely far apart. A gas can have a very high temperature while containing so little matter that it transfers almost no heat to a spacecraft. The same principle is why parts of Earth's thin upper atmosphere can reach high temperatures without behaving like a furnace.
So the wall of fire is a dramatic label for a real result. The plasma was hotter than expected, but it creates the wrong mental picture. Voyager crossed a thin, dynamic boundary region, not a blazing barrier. Another exaggerated claim is that Voyager discovered the heliosphere may suddenly fail, exposing Earth to lethal cosmic radiation. The heliosphere does help reduce the flux of lower-energy galactic cosmic rays entering the planetary region. Voyager's measurements beyond the heliopause have been essential for understanding what the unmodulated cosmic ray environment looks like, but the spacecraft did not discover that Earth is about to lose this protection.
Earth also has its own magnetic field and atmosphere. The shape and strength of the heliosphere can change as the sun moves through different interstellar environments over geological time, and researchers study how such changes could affect planetary habitability. That is a legitimate scientific question. It is not evidence of an approaching catastrophe. The genuinely unsettling part of Voyager's story is not a hidden threat. It is how little direct information we possess. Two probes, launched in the same year and moving in only two directions, have sampled an enormous three-dimensional boundary. From those two tracks, scientists are trying to understand the shape of a structure larger than the planetary system. Models disagree on whether the heliosphere has a long, comet-like tail, a more compact shape, or two broad lobes influenced by magnetic fields and charged particles. Voyager can tell us what happened along its path. It cannot photograph the entire heliosphere from outside, and the only instruments still collecting data aboard Voyager 1 are slowly disappearing. At launch, each Voyager spacecraft produced about 470 watts of electrical power from 3 radioisotope thermoelectric generators. These devices convert heat from the decay of plutonium-238 into electricity. The output falls by about 4 watts each year. By 2023, each spacecraft was producing roughly 225 watts, less than half its launch power. To keep the mission alive, engineers have turned off heaters, backup systems, and scientific instruments one by one.
In February 2025, NASA shut down Voyager 1's cosmic ray subsystem. On April 17, 2026, the low-energy charged particle instrument was also turned off to conserve power. As of mid-2026, Voyager 1 has two operating science instruments, the magnetometer and the plasma wave subsystem. The instrument that helped confirm Voyager's crossing is now one of its final two scientific senses. Every bit of data must travel through a transmitter producing only about 23 watts, comparable to a small refrigerator light. By the time that signal reaches Earth, its power is only a tiny fraction of a billionth of a watt.
NASA hears it through the Deep Space Network, giant antennas located in California, Spain, and Australia, spaced around the planet so that Earth's rotation does not permanently carry Voyager below the horizon. The largest dishes are 70 meters or 230 feet across. The data rate is usually measured in hundreds of bits per second. A modern internet connection can move more information in a fraction of a second than Voyager may transmit during an entire day. The fact that the link still works is not only a triumph of the spacecraft. The ground system has been upgraded repeatedly since launch. Antennas were enlarged, receivers became more sensitive, and new error-correcting techniques allowed engineers to recover information from signals that would once have been unreadable. Voyager survived partly because the technology on Earth kept improving around it.
Communication is also extremely precise. The spacecraft's high-gain antenna is about 12 feet or 3.7 meters across and must remain pointed toward a moving Earth. A small angular error can send the narrow radio beam past the planet. In 2023, a command accidentally shifted Voyager 2's antenna about 2 degrees away from Earth, and contact was lost. NASA used a powerful deep space network transmission, described as an interstellar shout, to command the probe to turn back. The answer arrived after a round trip of roughly 37 hours. Distance turns every repair into a slow-motion experiment. In November 2023, Voyager 1 stopped returning readable science and engineering data. The radio carrier was still present, which meant the spacecraft was alive and its antenna was still pointed toward Earth. But the information inside the signal had become repetitive, unusable code. Engineers traced the problem to corrupted memory in the flight data subsystem, the computer responsible for packaging data before transmission. About 3% of its memory was affected, likely because a single chip had failed. There was no possibility of replacing it, so the team performed a repair through radio commands sent across more than 15 billion miles.
They divided the affected software into pieces, moved those pieces into different available areas of memory, and adjusted the code so the separated sections could still work together. Each command required almost a day to arrive. Each response required almost another day to return. One diagnostic exchange could consume nearly 2 days. By June 2024, Voyager 1 was again returning usable data from all 4 instruments that were active at the time. The recovery sounded almost impossible, but it was not supernatural. It was careful engineering performed under extreme delay on a computer architecture from the 1970s.
The same is true of the strange telemetry episode in 2022. Voyager began returning impossible orientation data, even though its antenna was clearly still aimed at Earth. NASA eventually found that the attitude control system was routing telemetry through a computer that had stopped working properly years earlier. Engineers changed the routing, and coherent data returned. There was no evidence of an alien signal, no wormhole, and no unknown force turning the spacecraft around. These explanations may sound less dramatic than the viral theories, but they reveal something more impressive. A machine almost 50 years old can fail in ways its designers never predicted, and people on Earth can still understand it well enough to bring it back. Now, Voyager 1 is approaching 1 light day from Earth.
On November 18, 2026, according to NASA's current trajectory estimate,
The probe will be about 16,904,799,096 miles from our planet. A command transmitted at 2:16 in the morning Pacific time would not reach it until the same time the next day. The earliest possible reply would arrive another day later. The spacecraft will not detect anything special at that moment. One light day is a human milestone, not a physical boundary. Voyager will continue through the same thin plasma, measuring magnetic fields and plasma waves for as long as its remaining power allows. NASA cannot give an exact date for the final signal. The mission may continue into the 2030s if engineers can preserve enough electrical power and keep the communication system operating. Eventually, however, the transmitter or the remaining instruments will fall below the energy they need.
Then Earth will listen and hear nothing. Voyager itself will not stop. With almost no friction in interstellar space, it will continue orbiting the center of the Milky Way. In more than 38,000 years, it will pass within about 1.7 light years of a star known as AC +79 3888. That is not close enough to enter the star's planetary system, but it is close by interstellar standards. Attached to the spacecraft is the Golden Record, a gold-plated copper disc containing images, natural sounds, music, and greetings in 55 languages. It was never a serious attempt to begin a conversation on a human timescale. The probability of the spacecraft being discovered is extraordinarily small. The record is better understood as a time capsule and a statement of intent.
It says that a species on a small planet learned enough about nature to build a machine, send it past giant worlds, and release it into the space between stars. So what did Voyager detect at the edge of the solar system? Not a visible wall, not an alien craft, not proof that physics is broken. It detected a boundary more irregular and dynamic than the simplest models predicted. It found a sharp transition in particle populations, interstellar plasma denser and hotter than expected, a magnetic field that did not rotate as clearly as anticipated, and a persistent plasma emission that now allows scientists to trace density variations in the space between stars.
And what would Voyager see if its camera could turn around? Almost nothing that looks dramatic. A black sky, familiar constellations, the sun reduced to an intense point of light, Earth completely lost inside that point. But its instruments reveal what the camera cannot: the invisible weather of interstellar space, the pressure of the galaxy against the sun's protective bubble, and the physical boundary between the environment created by our star and the much older material beyond it.
Voyager's greatest discovery may be that the edge is not an ending.
It is a region of exchange. Solar disturbances can cross it. Interstellar particles press against it. Magnetic fields bend around it. Waves move through the plasma outside it. The solar system is not sealed off from the galaxy. It is immersed in it. And somewhere, almost one light day away, a machine built in 1977 is still listening.